Thank you very much. Um, so yes, my plan today, I was a bit hesitating which subject to choose for the workshop, but given the topic of uh, uh, resurgence and modularity in QFT, I thought a nice topic for the talk would be 3D modularity, looking at some uh, old results, but from a new perspective. So a lot of what I will say will be review, and some people will be very familiar with some of these aspects, but I will highlight what are the new elements in the story. So here, at the center of the story is a family of invariants, which were of topological invariants of three manifolds, which were defined as certain Q-series expansions with nice integrality properties, and which are interesting from a number theory point of view because they give examples of quantum modular forms. But then these invariants, they sit within a wider network of relations where they have been related, the same Q series have found an interpretation from the point of view of logarithmic vertex operator algebras. And then by the 3D correspondence, they have been identified with a half index for certain three-dimensional SQFTs. So now what I want to tell you about today in particular is related to this arrow between the three-manifold invariants and characters of logarithmic vertex operator algebras, or what I've written here, cone VOA. And the best place to start is then from the point of view of 3D topology. So here, the old story, which is already decades old, starts with uh, an invariant, a topological invariant for a three manifold, which from the physical point of view was defined as a partition function of 3D Chern-Simons theory at a certain level K. And then mathematically, it was formalized through the work of Reshetikhin and Turaev, getting a definition from the point of view of quantum group theory, and therefore becoming known as the WRT invariant. Now, the WRT invariants, they are numerical invariants. And the more recent challenge has been to find a new type of invariance for three manifolds, a new family of invariants that would categorify the numerical invariants. So this is why the new invariants are Q series in a formal parameter Q, which lives inside the unit disk. And the categorification looks at replacing the original numerical invariants with a more sophisticated structure of spectral sequences of vector spaces whose dimensions are captured by the integer coefficients appearing in the Q series expansion. And then the question, and okay, the reason for wanting such a categorified invariant in the first place came from a proposal in low-dimensional topology that such invariants could hold a key to solve some important questions. But then the question was how to approach this problem. Well, one possibility comes from M-theory, precisely using the 3D correspondence. Because starting with a stack of M5 branes, a twisted compactification on the relevant three manifold produces a 3D SQFT in the remaining three-dimensional space-time directions. And then here, the partition function of this 3D SQFT, which when the space-time background is in the shape of a cigar, it is called a half index or homological block. And it is related to the WRT invariant of the auxiliary three-dimensional manifold. And the partition function, it is labeled, it has an index which corresponds to a supersymmetric boundary condition on the boundary, and it counts the dimensions of graded vector spaces of BPS states. So from the physical point of view, the vector spaces of BPS states should be those that categorify the WRT invariants. And now it is possible to compute the half index using supersymmetric localization, which gives a prediction for the form of this invariant in the form of a certain contour integral. However, supersymmetric localization requires the existence of a Lagrangian description for the 3D SQFT. And this does not always exist. There are certain elements for which it is not known. So this approach from the point of view of physics does not always lead to a computational algorithm for the invariants. However, the intuition obtained from the type of contour integral that appears from localization combined with the expected relation to WRT invariance, this has led to a proposal for a computational algorithm for a type of tree manifolds based on some combinatorial data that specifies this tree manifold. So now I will review what this combinatorial data is, what the algorithm is that was discovered, and some of the structure of these invariants, and then say what is new now in this story. So very briefly, the type of manifolds for which these invariants have been, the algorithm has been proposed are plumbed tree manifolds, which can be realized by dense surgery on a set of links with certain weights that correspond to the framing. The same data can be encoded in a corresponding plumbing graph with nodes corresponding to the links and connecting edges, and with a weight function that encodes the framing. And this data can be translated into an adjacency matrix. So this class of manifolds contains, for example, cipher fibrations over a two-sphere, where the cipher manifolds, they are specified by a set of invariants corresponding to the exceptional fibers. And then the set of invariants, they are related to the corresponding integer weights of the leg and the plumbing graph by continued fraction. And particularly nice examples of such manifolds that are discussed whenever people discuss the Z-hat invariants are the Briskron spheres, which have the property that their plumbing graphs are in the shape of stars with three rays, so three-star plumbing graphs. And they are specified by three relatively co-prime integers, and their adjacency matrices are unimodular. So here I just gave the example of the Briskron sphere sigma 237, which is one of the easiest ones to analyze with its corresponding plumbing graph and adjacency matrix. And for such manifolds, the algorithm that was proposed to compute the three manifold invariants is in the form of a contour integral, where the integral is over the parameters z associated to the nodes of the plumbing graph, and it is defined by the adjacency matrix, which enters through a lattice theta function. And then the integral produces a family of invariants, which are labeled by elements A, which are in the co-kernel of this adjacency matrix. Now, for the example, sigma 237 that I had on the previous slide, it is very simple to compute even by hand what the invariant is. There's only one invariant. And performing the integral and regrouping terms, it was observed that the invariant is proportional to a linear combination of false theta functions, which all have the same index equal to 42. And where the false theta functions are one of the most simple examples of quantum modular forms. Now comes the caveat. I said that the definition was given for a certain type of tree manifolds, of plumb tree manifolds. And the caveat is that these have to be weakly negative in the sense that the adjacency matrix needs to be negative definite on the subspace of vertices connected to three or more edges. This is so that the resulting Q series produced by the integral are convergent. But with this constraint in mind, it was observed that for plumbed tree manifolds with three-star plumbing graphs, the corresponding invariants are in the linear span of a set of false theta functions, which all have the same index, which is simply determined by the combinatorial data of the manifold. And now the relation to WRT invariants, well, there are two directions that one can go. In one direction, it is possible to start with the tree manifold invariant and then a radial limit in the formal expansion parameter Q, which takes tau to a rational point, followed by a linear transformation on the set of invariants, recovers the WRT invariant. And then in the other direction, an expansion around a linear into a summation around a billion flat connections of perturbative series, starting from these and applying resurgence, doing a Borel summation, following by the inverse linear transformation, recovers the z-hat invariant. And now one can make a series of observations, and these give rise to three questions. So first of all, the fact that the three manifolds being considered are weakly negative definite gives rise to the z-hat invariants being proportional to special linear combinations of false theta functions. And the the question that comes up is what happens when the weakly negative definite manifolds get replaced by positive counterparts? And then related to this question, another important one is what happens to the vertex operator algebras that one finds? Well, the answers to these questions, for the first question, this I have discussed in previous talks that I've given on this topic, the fact that there exists a hidden modular symmetry that governs the building blocks of the z-hat invariants, the false theta functions. And this gives a hint on how to generalize the definition of the z-hat invariants, specifically to include the defects. Now, to answer the second question, this is a rather difficult question. It involves going to the other side in a way. So combining the structure from this Val symmetry and the relation to the WRT invariants, it is possible to find pairs of invariants, false mock pairs, where the invariants for weakly positive manifolds are related mock modular forms. And mock modular forms written specifically as regularized indefinite theta functions. Now, I said that this question of going to the other side is notoriously difficult, or at least it has been, because many attempts have been made across the years to give a proposal for computing these, and they all have relative advantages and obstacles. Now, recently, there has been a lot of progress. However, the one question of finding the corresponding VOA has stayed elusive. So this is where this precise formulation through regularized indefinite theta functions has an advantage in that it allows to construct the associated VOAs, these cone VOAs, for the manifolds that are weakly positive definite. So then the plan for the talk is then that I will review very briefly this hidden modular symmetry of the z-hat invariants, the Val representations, to motivate the definition of the defect z-hat invariants, and I will explain what their structure is. I will then have a very, very brief interlude on vertex operator algebras, specifically with the goal to introduce a definition of log VOAs from lattice vertex operator algebras. And then I will discuss going to the other side where formally, based on the relation to the WRT invariants, reversing the orientation of the manifold can be seen as same as going from the upper half plane to the lower half plane. So I will explain what effect this has on the false invariants, how they are related to mock modular forms, and specifically mock modular forms, mock defect invariants as regularized indefinite theta functions, and then show how these lead to cone vertex operator algebras. So starting with this hidden modular symmetry that I was discussing, the Val representations. Now, these can be constructed as unitary representations on the space of Jacobi theta functions. So one starts with a vector of theta functions with some index greater than 1, and labels R running modulo 2m. And this vector spans a 2m dimensional representation of the metaplectic group. And this representation is reducible because it is possible to construct irreducible, but more generally sub-representations as the simultaneous eigenspaces with respect to some elements of an orthogonal group which have an action on the theta functions that commutes with that of SL2Z. And now concretely, it is possible to construct sub-representations of this larger one using an isomorphism between the orthogonal group and the group of exact divisors of the index, which is implemented by some matrices called omega matrices. And then in practice, these sub-representations are constructed as, well, they are defined as the simultaneous eigenspaces of some elements in the orthogonal group corresponding to a subgroup of the group of exact divisors which have eigenvalue 1. And the sub-representations are constructed with the aid of some projectors defined in terms of the omega matrices for those integers. And applying this projector to the original term-dimensional vector gives another vector which contains only a subset of the original theta functions and which gives a basis for the sub-representation. So concretely, if we take the example of the integer m equal to 42, and this subgroup of the group of exact divisors containing 6, 14, and 21, and we apply the corresponding projector from the previous slide to the vector of weight 3 half theta functions, the result is this other vector, which contains only 3 linear independent components, linear combinations of theta functions, with the observation that if a particular set of functions appears in one of these linear combinations, it does not appear in any of the other. And now the relation to the z-hat invariance, it was observed already in the example that I mentioned explicitly for sigma 37. I said this was proportional up to an overall rational power of q to this specific linear combination of false theta functions. Well, this is precisely the first, it corresponds to the first entry in this vector, the relation just being taking the holomorphic Eichler integral. And then the same structure continues to hold for Briscorn spheres in general, where the index and the subgroup of the group of exact divisors are determined strictly by the plumbing data, and the same for the label R. But now here comes the first question that I asked. Given that in the sigma 237 case, there is only one invariant that appears, and here there are 3 Val orbits, I will refer to these as, because it's much simpler than saying linear combinations every time. What about the other Val orbits? How do these appear? So this motivated introducing, expanding the definition of the invariance to include defects, where the defects are supposed to account for Wilson loops inserted on links at the nodes of the plumbing graph. Now, these Wilson loops, they have a representation associated to them, a representation of the Chern-Simons gauge group. And because we are secretly working with rank 1, these representations, these highest weight representations, are specified by one integer parameter, w. Now, the effect on the definition is to insert the corresponding character into the integrand. So this is just a Laurent polynomial in the parameter z associated to the corresponding node in the plumbing graph and defined by the corresponding highest weight label. And the second modification is an additional shift in the lattice summation, which is defined by the integer highest weight parameters. The reason for introducing this additional shift is such that all defects would have a non-zero defect invariant associated to them. With the original definition, some defects just had a 0. And now, with these, the first observation is that with this definition, this enlarged definition for the defect invariance, this really is a topological invariant of the 3-manifold because it is invariant under 3D Kirby moves on the plumbing graph, which are local changes to the plumbing graph that leave the topology invariant. but which also preserve the nodes at which defects are supported. So the proof for this is entirely analogous to the one that originally appeared in the paper of Sergey and Ciprian a few years ago. Now with this, returning to the simple example of the Briskon sphere sigma 237, this is the original invariant without any insertion of Wilson loops. If one places a Wilson loop at this node with uh, with label -7, with framing label, and takes the highest weight label for the Wilson loop be 1 or 2, the result is precisely the remaining two val orbits that appeared in the previous slide. And so these three together form an SL2Z vector valued quantum modular form. Now the important point to note is that the same index appears in all cases. And now so far I just gave two examples. I said I specified the node and gave two weights. But the point is that taking any of the nodes and taking any weights for these end nodes, the resulting invariants will be in the linear span of these three false theta functions. So this is part of a more general statement, which is a theorem, which states that the defect invariants for Briskon spheres with Wilson loops with defects placed at the degree 1 nodes, these span the components of an SL2Z vector value quantum modular form, where the index and the subgroup of the group of exact divisors are determined only by the manifold itself, not by the defects. And the labels of the false theta functions are determined by the manifold and the defect data. So there are two modular structures that appear here. One acts on the set of the z-hat invariants with the defects included. And the other one is the quantum modular structure with respect to the modular parameter tau. And this statement is for Briskon spheres, but in the paper that was published a little over a month ago, we have an extensive analysis for many more Seifert manifolds. This is just a short excerpt of the table, and the same structure continues to hold. So now I want to focus on the second arrow, which connects the topological invariants with linear combinations of characters of Fagan-Tipunin logarithmic vertex operator algebras. So this is where I wanted to have a brief interlude about VOAs, which starts very, very broadly. So the VOAs, the intuition for these is that they formalize the idea of having operators inserted at points on a Riemann surface and which get multiplied by operator product expansions. And the definition takes a set of data which contains a graded vector space, which contains a distinguished vector element and a conformal vector, as well as two linear operators, a translation and a vertex operator map. And these satisfy a set of axioms. And because the space of states V has a grading, it is possible to associate a character to it, a formal Q series that keeps track of the of the subspaces with fixed grading, with fixed weights. And then similarly, a V module is another vector space with a similar vertex operator map, such that all the axioms of the original vertex operator algebra that still make sense, they continue to hold. And similarly to the space of states, there is a character associated as a formal Q series expansion to the module. And now, examples of these, the most simple example of a VOA that one can take is the Heisenberg algebra. So the Heisenberg VOA is associated to the Heisenberg-Lie algebra, and it is defined in the space of state is defined in terms of the universal enveloping algebra, and it is spanned by a set of vectors formed by certain monomials acting on the vacuum, which determine the weight of these elements, and for which the character of V turns out to be just the inverse of the Dedekind data function. Then going slightly more generally, there are the affine VOAs, which are associated to finite dimensional Lie algebras, where the space of states is defined in terms of the universal enveloping algebra of an affine extension. And the third example that I wanted to mention is precisely that of lattice VOAs, which are associated to lattices defined by a basis of vectors, which have a symmetric bilinear form. And if this bilinear form is positive definite, then the resulting vertex algebra is a vertex operator algebra. Now, in terms of the lattice, it's possible to define a Lie algebra structure and then define the space of states of the lattice VOA analogously in terms of the universal enveloping algebra tensored with a ring. Now, the reason for putting these three examples up is just to say that so far all known VOAs can be constructed starting from affine VOAs by taking by iterating some standard constructions, by either looking at some invariant subalgebras, taking cohomologies, or taking certain extensions. And now the old story here concerns the representation theory of rational VOAs, where rational VOAs contain only completely reducible Z-gradient modules. They have only a finite number of inequivalent irreducible modules with finite dimensional graded components. And then an old theorem of Zhu, which is almost 30 years old now, is that for rational VOAs, which satisfy some finiteness condition, then the characters of the inequivalent classes of irreducible modules span a vector space that is invariant under an action of SL2Z. So these form a vector valued modular form. Now, the newer story concerns non-rational VOAs, which have a few defining features. For example, the appearance of logarithmic divergences or singularities in the OPs. And from a representation category point of view, theirs is more interesting because it contains modules that are reducible but indecomposable. And here, the Fagin-Tippunen log VOAs, these are defined for finite simple Lie algebras of ADE type and a positive integer m. And when G is just SL2, then the Fagin-Tippunen algebra is referred to as the triplet 1, m algebra. The construction for these starts from a lattice VOA with the lattice specified by a rescaling of the integer line. And then in terms of this positive integer, two parameters are defined. And then these two parameters enter the definition of two screening charges in terms of an exponentiated vertex operator map. And then the triplet algebra is defined as the kernel of the lattice VOA associated to L of the screening operator Q minus. Whereas from the triplet algebra, a second logarithmic vertex operator algebra is defined as the singlet from the restriction to the Heisenberg VOA in the lattice VOA. And here there's the interesting departure from the representation theory for rational VOAs in that the singlet algebras, they contain modules called atypical modules whose characters are proportional to false theta functions. So now combining from the previous slides the fact that defect invariants are proportional to linear combinations of false theta functions, where the index is fixed by the manifold data and nothing else, and the labels depend also on the additional defects, and the fact that false theta functions with a certain index are proportional to the characters of 1, m singlet log VOA, it is now possible to associate a singlet log VOA to each three-manifold that has a three-star plumbing graph that satisfies the constraints we had from the beginning, and therefore to a defect invariant. And now this relation on its own might seem like a bit of a coincidence, like an accident, because false theta functions are still rather simple. But the fact that this relation continues to hold at higher rank, so when in the other direction of generalizing these invariants that I'm not discussing today, there it's highly non-trivial to find such a relation. So it's not an accident. And now this relation to log VOAs has interesting implications. From a physical point of view, what it suggests is that the boundary VOA of the or 3D SQFT on the cigar-shaped background should be related to a Fagan-Tipunin log VOA, and that these log VOA should categorify the half index and the WRT invariants. But now there are still, the picture is still rather incomplete in the following sense. For higher rank Lie algebras or for general three manifolds which do not satisfy the weakly negative condition that I mentioned in the beginning, there is much that is still unknown despite a lot of research in the field. I could not fit all of the references that study this onto one slide. For example, here, an issue is that the series expansion, the structures of the series expansions referring to the modular structures are more obscure in these other cases. And for the three manifolds that do not satisfy the weakly negative definite condition, a similar mathematical definition to the negative definite counterpart does not exist. I put here an important asterisk because it is possible to compute these invariants, at least numerically. So I will come back to this point in a minute. But for now, I just want to give the example because we were looking at the Briscorn sphere sigma 237. Reversing the orientation of this turns it into a positive definite manifold by simply changing the sign of entries in the adjacency matrix. And now coming back to the expectation, from the point of view of the 3D Chern-Simons theory and the WRT invariants, formally starting from the integral definition of the WRT invariants, changing the orientation of M3 is equivalent to changing the sign of the level K. So one would expect that for the Z-hat invariants, changing the orientation would be the same as changing the sign of tau. However, the reason I said that this is problematic is that in general, this leads to divergent Q series. It is possible in certain circumstances to make sense of these if there is a nice hypergeometric form for the function or there's something special happening. But in general, they are divergent. So then the question is how to go to the other side. And in particular, the point that I stressed in the beginning, how to do it in such a way that we find an analog for the second arrow, what appears here for the vertex operator algebras. So going to the other side, I said, was a very tricky endeavor, and people have attempted for a long time to do this. And the various attempts, for example, using analogous invariants, but not associated to closed ring manifolds, but to knot complements, they have produced some successful results. So they were encouraging, but they also had their limitations in the sense that they were producing Q series where either a modular structure was not unknown or the VOA is a mystery. Well, more recently, there was the work of Ovidiu, Gerard, Angus, and Sergey, which produces a systematic computational approach. So it is possible to now compute these invariants for manifolds that are weakly positive definite. But still, the corresponding VOA remains a challenge. So now you will hear more about this later in the afternoon, if I'm not mistaken, in Sergey's talk. But what I want to talk now about is this alternative approach, which uses number theory. It relies crucially on the modularity properties of the invariants to construct the defect invariants in false mock pairs in a way that leads to a means to construct the corresponding VOA on the mock side. So on one side, the Z-hat invariants for weakly negative definite manifolds we saw were false theta functions. The partners should be related modular forms. Now these have a certain weight. They are holomorphic functions with a unique shadow such that the completion given by the difference with the non-holomorphic Eichler integral of the shadow is modular but not holomorphic. And examples that are salient, that are important, are the order 7 mock theta functions of Ramanujan. Because, well, on one hand, these have an expression in terms of Q-shifted factorials, and the shadows are precisely linear combinations of weight 3 half theta functions that occur in the combinations that appeared in the Weyl orbits that we saw earlier. Now, the relation to the false invariants come from a limit, an asymptotic series expansion, because the limit, as tau approaches a rational point, a cusp, of the bounded part of the mock modular form, produces a series expansion that is compatible with the analog of the holomorphic Eichler integral of the shadow. So now, the relation is that the pairs of invariants, the false mock pairs, should be such that they have compatible asymptotic series expansion in the radial limit, where the false invariant is proportional to the shadow of the mock invariant. And here there is an asterisk because this generalizes the previous expectations in that it's not, I put a tilde here because this is not on the nose equal, but it's rather equal to the non-vanishing or non-divergent part of the shadow of the mock invariant. So based on this expectation, the false mock conjecture, one would associate to the defect invariance that we saw earlier associated to the sigma 237 Briskern sphere, the order 7 mock theta functions of Ramanujan. We should therefore define or predict what the mock defect invariants are. And without insertions of any defects, this expectation was already proven a few years ago. But now the question is how to find such mock pairs systematically. And this is a tricky question because, for example, it is possible to look at Apple-Lurch sums and associate to every false theta function that is a building block of the defect z-hat invariance a partner in the lower half plane defined in terms of the Apple-Lurch sum. So it has a moderately complicated expression, but still manageable. And this is a mock modular form. It has a compatible radial limit, but computing it explicitly shows that at least for the sigma 237 example, the result is inconsistent with the known results using knot complements. So this should highlight how subtle this business of going to the other side is. The other approach that is tailored to constructing mock modular forms looks at regularized indefinite theta functions. So theta functions defined as Q series with summations over a positive definite lattice, they are convergent. If the lattice has an indefinite quadratic form, the series diverge. But it was shown in work by Svegers from roughly 20 years ago that it is possible to tame these divergences by introducing a regularization factor, which essentially is cuts out a cone on the summation lattice. It is 0 outside of the cone and constant inside. So then looking to find such a form for the mock defect invariance. Okay, I will just briefly mention that from this form for the regularized indefinite theta functions, it's possible to construct the shadow. But I will skip the technical detail and just say that looking for the shadows, so trying to find a function tailored to have a particular shadow, one can start naively with the original definition of the false defect invariant, integrate as usual to produce a convergent Q series, and then naively map to Q to Q inverse, which produces the divergent Q series. But then this can be multiplied by a mock modular form, which will produce an indefinite lattice, and then restrict the summation over the cone by introducing a regulator. So the choice of parameters to specify this theta function that we multiply by, and the choice of vectors that determine the cone and therefore the regulator, these are the crucial data. And here we have a proposal for the Briscorn spheres, for an infinite family of manifolds that sets um, the regulator data in terms of the entries of in terms of the relatively co-prime integers which specify the Briscorn sphere, and which indeed produce a modular form whose where the holomorphic integral, holomorphic Eichler integral of the shadow produces the original false defect invariance. I should put here again the asterisk that this holomorphic Eichler integral is taken on the non-vanishing and non-divergent part of the shadow. Now, the three important observations here are that the cone that appears on the lattice, it's specified only by the manifold data, so the defects do not play a role here. The Q series that are generated agree with expectations based on calculations using knot complements, but where the modular structure is not clear, these just give honest Q series expansions, so we just match order by order. And lastly, the defect invariants that appeared in this construction are therefore vector valued mixed modular forms. And in certain nice cases, they are pure modular, and it's spectacular when this happens. And now the last point to say is that because the regularized indefinite theta function is constructed with regards to a lattice, it is then possible to associate a VOA to the cone in the same way that VOAs are associated to lattice VOAs. In fact, defined by a restriction from the VOA associated to the lattice. And then on these modules, twisted modules can be constructed in terms of the data that includes the defect data and whose characters are precisely the mock invariants. So this rounds up the story in a rather pleasing way. I guess since I'm closing in on 50 minutes, I can skip the technical details on the construction of the lattice VOA and just come back to the big picture and the context. I started with 3 questions specifically about this hidden modular symmetry of the Z-hat invariants that led us to the defect Z-hat invariants, where these span the components of vector valued quantum modular forms. This led us to a proposal for mock Z-hat invariants as regularized indefinite theta functions. That also led to the definition of cone vertex operator algebras, analogous to the log VOAs of Fagin-Tipponen. And now this gives rise to a series of other questions. First of all, what can be learned from this structure of the defect invariants? Because these, again, sit in this wider context related to WRT invariants, to flat connections. What can be said about that? It's still important because it's still a simple class of manifolds for which we have defined the mock invariants. How can this be generalized to other types of M3? A big question, which is very bothersome, is that this relation between the false and mock invariants goes through Q series. A more fundamental relation would be at the level of vector spaces, so relating log VOAs to cone VOAs in a direct way. That would be particularly nice. And then lastly, something that we're looking into is relation to the resurgence results that have appeared recently. So thank you for your attention. Yeah. Very little, surprisingly little. These only exist in 2 papers in the literature for very specific cases. So we found those and found that we can generalize the construction to this case, but they're unknown for now. No, just they haven't been studied. They appeared in relation to moonshine, for example, but it's only John Duncan, for example, that studied these, and then now with Miranda Cheng's group, we have looked into them. So there is a lot of unknown territory. Mm-hmm. Yes, but you can choose anything you want, and then they would produce series with um so C1 is always 1 comma 0. This is simple because it gives on the nose exactly the shadow that you want. The other one is defined in terms of STR, the largest of the relatively coprime integers, and X, which appears in the choice of the function used in the regulating process, the modular form. There was only one example that was known before this paper. The other ones, with one of the students that I'm working with Davide, we have a code that computes systematically the shadow with all the simplifications, given some inputs. So we thought, as unelegant as it is, let's just brute force it and give some vectors and just try to see what patterns appear. And we spotted a nice pattern for manifolds that can be constructed as complements of torus knots, torus 2,3, so trefoil knots. And then it was just an educated guess how to expand, how to generalize this definition to other manifolds. Like it is natural. We had the sigma 237 and sigma 2313, which can be obtained from the trefoil knot with certain surgeries. So we could just see numerically, okay, these parameters work, and then we generalize the rest. The shadow is garbage. It's just it doesn't make sense. It has to be, like I said, at first we were very unhappy to see mixed mock modular forms appearing. We wanted pure mock, and we saw that if we change the data, it gets messy. That there's no pure mock; it's all mixed mock. But if we kept specialize here STR, so to have 2, 3, and 6R plus 1 is the only choice that will give pure mock modular forms. Oh, well, yeah. I mean that would be the next step. Yes, for the regularized indefinite theta functions, the extension exists. It's already in literature. For the false invariants, this is other work that I have with Miranda Cheng and her students, where we looked at the higher rank invariants and looked at what the corresponding shadow should be exactly by computing compatible functions. Yes, yes. So in that sense, it's natural. But this is the step before. That's already going much further, and already this at this level, the problem is complicated. Nah, I will refer you to the papers. That is a very long story, but it was the idea was to construct VOAs for that are related to moonshine modules. I think all of them. The idea was to there was one that appeared initially, and then Miranda worked on the other cases. I can show you the papers. So Yeah. We have not computed, so there I cannot comment yet. Thank you.